Now, I will go to the second lecture of week 12 of this course, and in this lecture I will introduce a very useful concept called the density of states, and later on we will see how this density of states can be used along with the band gap information to infer about the electrical and optical properties of the material. So, week 12 lecture 2 will be on density of states. So, now let us look at the density of states due to a single energy band first, okay, and then we will go to the density of states due to multiple energy bands. Okay. Now, if you have a single energy band, okay, then I am just showing schematically a relation between the energy and the wave vector. Okay. So, imagine I have a k here, and let me take, do not worry about the origin or origin in this k direction, just let us say this is the allowed range of allowed values of k, and if you plot this energy as a function of k, energy of just one band, okay, then you will have a graph that looks maybe something like this. Okay, so, maybe you have a graph that looks like this. Okay. And so this is energy of k, okay, is the band structure. So, the band structure is given by the energy as a function of wave vector. Okay. So, let me just write it down. So, the band structure is given by this relation E of k. In general, it is k is a vector. Okay. In general, k is a vector, but just for representation I will show it as though k is a scalar. K is a scalar, I will just show a one dimensional representation, but in principle k is a vector. So, now you ask a question, what is the density of states due to what do you mean by the density of states? Okay. Now, to do this we go back to the Born von Karman boundary condition, Born von Karman boundary conditions. Okay. What the Born von Karman boundary condition says is that if L is size of the system, that is of the crystal, the total size of the crystal is L. Okay. So, L is the total size of the crystal, okay. Then k in one dimensions should be n pi by L, okay, where n is an integer. So, in 1D, so this is in 1D, k should be n pi by L. That means the spacing between successive k values, that means implies that the spacing between successive k values is pi by L. Okay. So, pi by L is the spacing between successive k values, and what you say, each k value corresponds to a state. So, each k value, this is an important idea, each k value is an allowed state. Okay. So, you can have several different k values, okay, each of them is an allowed state, and according to the Born von Karman boundary condition, the spacing between successive k values is pi by L. So, what this implies is that in this band structure there are various states, okay, and I am exaggerating the size, okay, such that this spacing between any two states is pi by L. So, this is the k axis. So, on the k axis the successive states are separated by this pi by L. So, you could imagine that there is one allowed value of k here, one allowed value of k in each of these intervals, okay. And since L is very large, okay, these intervals are very closely spaced. I am just exaggerating the spacing between the intervals here, okay. Now, you can ask the question, okay, if you look at some some interval of energy. Okay, so if you look at some interval of energy, okay, let me call this d dE. Okay, how many k states are there? So the question is, so how many states are in interval of energy dE. So if you have dE is the interval of energy, and you ask how many states are there in this. Okay, and so obviously if dE is larger, then the number of states will be more. If d is smaller, the number of states will be fewer. So this number of states is represented by, so you can write this as so the number of states in energy between E and E plus d dE. Okay, so this is how you write it. Okay, the number of states in energy interval between E and E plus dE is some function g of E times dE, g of E times dE, and this function is called the density of states. So you take the number of states in some interval and you divide by the size of that interval, you will get the density of states. So if I just take dE to the denominator here, so I take the total number of states between the energy E and E plus dE, and I divide by that interval size, I will get the density of states. Okay. Now just by looking at this band structure, you can immediately see that that in this region, so if you take this region, okay, where the energy is changing very rapidly with k, you have very few states, whereas if you take the same interval in this region, you have more states. So if I call this interval dE1 and I call this other interval dE2, okay, you can clearly see that the density of states in dE2 is more, because the band structure is flat. So you have lot of states in this energy interval. Okay. Again you have to imagine that I mean I am showing only a few of these green dotted lines, but actually there are a lot more states. So you have several allowed states in this region, whereas here you have relatively few allowed states, because the slope is high. So the first thing you realize is that g of E in one dimensions is large in regions where slope of E of k is small. Okay. So this is a very important idea, that when the band structure is flat, that is the flat regions of the band will have a lot higher density of states than the regions where there is a lot of variation. Okay. Now the other point I want to make, okay, I am just going to erase this thing here to make this point, okay, is that often in the books and journal articles, what is done is the band structure is shown, and then side by side right here you show the density of states. Now the density of states is actually, because E is an axis for the density of states, so the g of E is actually plotted here. Let me erase this. So g of E is plotted this way. Okay. So so basically here you have no states, here you have a very large number of states, okay, and then the number of states is very low in this region. So here you have much smaller states, and that is shown this way. and again in this region the number of states increases, okay, and so you will get something like this. So, this is what the density of states looks like. Okay. So it's often plotted side by side with the band structure. Okay. So, again keep in mind a high density of states in this graph, high density of states is here because the density of states is in this axis. So, a large density of states is here. Here there is a small density of states, again because the slope of the band structure is large. Okay. And again at this end there is a large density of states. So you can, at least in this one dimension, your density of states will look like this. You can qualitatively argue this just by looking at the slope of the band structure. Okay. Now, there could be more interesting things. There could be multiple bands. Okay. Now, suppose you have a band structure that looks like this. Again, I will just for ease of drawing, I will just use a one dimensional representation. Okay. Let me show the E as a function of k here, and here I will show g of E. Okay. So, now suppose E as a function of k has something like this. Okay. Suppose you have multiple bands like this. Okay. So, now each of these states will contribute to the density of states. So, the total density of states, so this is the total density of states due to all the bands, due to all the bands. Okay. So, this total density of states will look like this. So, here it is 0, okay, then it goes high. Okay, because this is one band which has a very small slope. So, small slope we said that it means a high density of states, and then it goes down. Okay, then right around this point, so it goes down, and right around this point now you see a second band come. Okay. And this band has a smaller slope. So, you will see a slight increase in the density of states. Okay. Then again it will go down, and then you will see an increase on the states due to this third band. Okay. So you can have something like this, okay, due to all these. So here you have multiple bands contributing. So, you have a very large density of states, okay, and then it will go down. Again here due to the flat region you will see a high density of states, and finally it will go down. Okay, again it will increase due to this flat region, and then due to this flat region, and it will go like this. Okay. So you can get a much more rich behavior in the density of states when you have multiple bands. Okay. So, you can get a much richer behavior when you have when you have multiple bands involved and not just one band. Okay. So, the density of states in this case is due to contribution from each of the bands, and when all the bands contribute, that is where you would expect the highest density of states. So, in flat regions and in regions where many bands contribute. So, let me emphasize that this is region where several bands contribute. To the total density of states. Okay. So, this is the picture of the density of states due to multiple bands. Now, in 3 dimensions you can do the same thing. So if you are in higher dimensions, then you do not have a simple k vector. Okay. So, the band structure, now you can immediately see the advantage of the density of states. So, in the band structure, if you look at the E versus k band structure, okay, then you have, as we had already seen in higher dimensions, you have this whole path from gamma to x to L to W to again to etc. Okay, and you have to some other point. Okay, and so you have a path in K space. So you have a path in K space. Okay, but the nice thing about the density of states. Okay, so the band structure in some sense depends on what path you take. So this band structure, however, you might get something like this. You might get some complicated behavior, and this band structure really depends on what path that you take. So the band structure depends on path, but the density of states, okay, that does not depend on the path taken. I mean, density of states just counts the total number of states. Okay. Now, what is important here is that you might not see all the bands at any place. So, depending on the path taken, you might not see some of the bands. Okay. So, the density of states, okay, you will get some information that looks okay. And the point I want to make is that there might be paths that are not seen. Okay. So, so this contains information about the states that may not be visible in chosen path for band structure. This really illustrates why the density of states is a useful quantity. Okay, so the band structure really depends on the path that you choose, whereas the density of states, this looks at all possible paths. It just looks at all states. Okay, now some of these states might be in along different paths. Okay, as we had said, the path in K space basically sets a certain direction in which you are allowing the wave vector to vary. Okay, but really if you look at the Brillouin zone, there are a lot of wave vectors that are allowed states which do not fall on the path. Okay, which do not fall down on the path in higher dimensions, and so those states will also contribute to the density of states. Okay, so the density of states, in some sense, it contains a lot more information than the band structure along a chosen path. Okay. Now, formally, how do you understand the density of states? Okay, so we said that we need to write the number of states between E and E plus dE as g of E dE. Okay, so so we had the idea that the number of states between energy E and E plus dE is equal to g of epsilon g of E dE. Okay. Now, how do we go about calculating this g of E in the case of higher dimensions? Okay. Now, there is a way to do this by essentially converting this to an integration over volume. Okay. So, we use the idea that in K space, okay, number of points, okay, this again comes from the von Karman boundary condition, okay, and this is equal to L by A cube. Okay, if you just take for a cubic system, this is for cubic system. Okay. And what that means is that the density of points in K space of points, that means for every, as we already saw this, we saw that every pi by L, okay, pi by L in interval pi by L in 1D we had 1 K point. So, in 3 dimensions you have pi by L cube, you have 1 K point. Okay. And if you use this information, okay, and you convert this to an integral over K, and now what you will see is that if you want the density of states, then at any point, then you have to consider one small region around that energy. So, suppose I want the density of states at this energy, okay, let us say this is my E, then I basically consider a small shell around this. This is an energy shell, okay, this is D of size dE, and I count all the states in this region. Okay, I basically count all the states that are in this region. Okay. And so I count the states coming from here, from this, all the states coming from here, and from here. Okay. So, I count all these states and I get the total density of states. So, now this can be written as an integral in K space, okay, integral over the K space, okay, and using certain mathematical techniques, this can be expressed as an integral over a surface of constant energy. Okay, this is a surface in K space of constant energy, okay, and what you have is you have a d ds, okay, this is the surface element, okay, and divided by 4 pi cube, and you have 1 over absolute value of, and you have the gradient in of E of k. Okay. So, this is the again this derivation is slightly complicated, okay. I am not going to do this in detail, but the idea is that you this is the gradient is like dE by dk, okay. So, this is dk by dE, okay. So, you are writing this in terms of this gradient in K space. So, as we said, when the gradient is large, okay, that is the slope is very high, okay, then you have very few states, okay. So, when the so it is inversely, so this is exactly the same statement in 1D where we said that a small slope, okay, leads to a large number of points, okay, whereas a large slope leads to a few number of points, few number of states. So, the number of states is actually it can be expressed as a surface integral. This is a surface of constant epsilon. So, this is actually a surface in K space, okay. So, this is a surface in K space of constant epsilon, okay. So, constant energy E. Okay. So, this is a surface in K space of constant energy E, okay, and so this G of E is written as an integral, and this integral is over this surface, okay. So, you basically you look in K space and you look at a region in K space where the energy is just E, okay. So, if I show it schematically, okay, let me just erase some of this just to show it schematically. Okay, I will just erase this region just to show it schematically. So, if you look in K space, okay, so this is your coordinates of K, okay. So, K, you can think of this as Kx, Ky, Kz, okay. And now if you ask what is the surface of constant energy E, okay, so there will be, if you say that energy should be equal to E, okay, and you look at that region, you will get some surface, okay. and if you ask what is the surface where the energy is E plus dE, okay, that will be another surface. Okay. And basically what you are doing is you need to calculate the volume of this region, okay. Again this is in K space. So, you are saying you want to know how many states are there. So, that is the number of states can be expressed as the volume of this region times the density of points. Okay. So, if you multiply the volume by the density, you will get the number of states. Okay. And so the idea is that you need the volume of this region in K space, okay, and that volume of that region, okay, can be written, okay, using Green's theorem. This can be converted to an integral over this surface. So, this is the surface of, I will just shade it in a different color. This is the surface of constant energy E. So, this integral over this volume can be written as a integral over this surface of constant energy E. Okay. And it turns, and if you work this out, okay, it's not a very difficult exercise, but if you work it out, then you can see that what you have is a surface integral, an integral over this over this surface. Okay. So, you look at the gradient. This is a gradient in K space. That means this gradient in K is expressed as okay. So, this is mathematically, this is expressed as I times dou E by dou Kx plus J times dou E by dou Ky plus K times dou E by dou Kz. Okay. So, this is the expression for the gradient, and using this expression you can calculate the density of states in higher dimensions. Okay. Now, I should mention this just for completeness, that I could ask for the contribution to the density of states due to the single band. So, if I just look at one band, let us say I just look at this band and I just look at the density of states only due to this band. Okay. So, I ignore all the other bands. Okay. Then the density of states due to this band will look something like this, okay. And this is sometimes referred to as Gn. Okay. So, this is density of states or sorry, G of En. Okay. So, the subscript E. Okay. So, this is the band index. Okay. So, this is the density of states due to this band, and what you can see is that if you add up the density of states due to each of the bands, you will get the total density of states. So, the total density of the states is the sum of density of states due to each of the bands. Okay. Again, the idea is the same. You can use density of states due to one band, or you can use the total density of states. It will follow exactly the same procedure. Only if you have just one band here, if you just want the density of states due to one band, so then you will have En here and you will have an En here. That is the only difference, and you will have S of En. With this, I will conclude this lecture. I hope I have given you an idea of the usefulness of the concept of density of states. I do not this is very widely used in electrical properties of materials and electrical and even optical properties of materials. We will see a couple of applications, but I just wanted you to know that there is this quantity called density of states, and what is the physical meaning of that. So, the exact formulas, I mean, they obviously depend on the band structure. So, if you want to calculate a density of states, you need the band structure, you need information of how the energy changes with the wave vector. Okay. We will just be doing it qualitatively, like how we did. We look at the slope of the diagram and then we look at the approximate, we just try to qualitatively sketch the density of states. However, we will see in the next class that the information that we get from the band structure and the density of states can be used to understand the electrical and optical properties of a material, of a solid. So, with this I will conclude this lecture. Thank you.